Okay, yeah, thanks, Mike. So I hope you can see my screen.
Yes.
So the aim of my talk today is to actually present you an overview over all the results we achieved for the fractional PDEs in the last 1.5 years. And this is joint work with a lot of people, and one of them, this is my colleague, and the other one is my PhD supervisor, Jens Markus Melenk, and other guys from Austria, Marian Pavisi and Dick Pretorius. Okay, so the outline of my talk is, since I guess not everybody is familiar with everything I'm talking about, so I will take some time to explain everything in the title. Then I will give you the precise mathematical definitions, and then I will go through the 3 parts I actually stated in the title, so optimal additive FEM, preconditioning, and local analysis. Okay, so let's start with explaining the title. I mean, Mike said you're working with fractional operators, so maybe this slide is not necessary, but why are we actually interested in fractional powers of differential operators? So maybe an application is, if you think about the random walk with a fixed jump size, so you can only jump with probability 1/2 to the front or probability 1/2 to the back. And if you take some kind of limits, so making the steps arbitrarily small or whatever, you would get something. You can describe this process by the heat equation. So in the sense that you would get the Laplacian, which governs the motion in space. But if you would allow arbitrary long jumps, so you can jump very, very far away, but with a little probability. So any jump is possible in both directions, as I draw here. And you would take some kind of limit process, then you would get the so-called fractional heat equation. So in the sense of the fixed jump size, you would get some kind of a Brownian motion, which can be governed by the Laplacian. And for the arbitrary long jumps, you would get a motion which is governed by a Levi process. And the generator of a Levi process is a fractional Laplacian. So this is from a motivation from probability theory. In physics, it would give you some additional parameters for more refined models. And this is used in non-local physics, where we have some anomalous diffusion processes which cannot be governed by a Laplacian or a heat equation or something like that. But you need some more refined models which somehow more capture this non-local effects. This is also used in image processing, finance, or material science. So right now there are many applications for that. I'm a mathematician, so for me, it's fun is that it's a non-local operator. So non-local effects are, especially in numerics, challenging. And it's always nice to work in currently active research fields. So nice that there are a lot of papers and a lot of progress is made in this field. Okay, so this was about the fractional operators. So I'm a numerical analysis. So I actually do finite elements. So what is the idea of finite elements? So here's a picture of me. And the idea of finite elements is to decompose the picture into triangles, or generally compose something into triangles, and then compute an approximation. Here is an approximation of the grayscale on each triangle. And then you get an approximation of your, let's say, continuous object by something discrete. And this is the idea of the finite element method in a nutshell. But this is a bad approximation, you would say. I mean, the picture on the right does not look at all as me on the left. So the idea is to just make the triangles smaller. Then you get some more refined information. So I only draw the lines of the triangles, not the fillings. Okay, so making smaller triangles, we still don't see anything. Smaller triangles, smaller triangles, smaller triangles. Now you can see that they somehow capture the information better. By using smaller triangles, I can get the information locally better. So, okay, and then you can see that this closely resembles me again. But it's a discrete object, so something which we can compute on the computer. Here I actually split each triangle into 3 more. This is what I did here by making my approximation better. But you can ask, is this clever to do this everywhere? maybe I only use this refinement, so the splitting of the triangles where it's actually needed. So doing this in a different way, so just this is the idea of so-called adaptive finite element method. This is one thing I presented in the titles. Adaptive finite element method is I just use this refinement of the triangles, so splitting into sub-triangles, where it's actually needed most. And doing this a few steps, you will get a completely different picture. So you would get this picture. This is now computed with a refinement only where it's needed. And comparing it to the picture before, so both pictures have roughly the same number of triangles, but the picture on the right actually has more refined information where actually change is in color is happening. So at the eyes, at my beard, at my t-shirt, at my hair. But on the outside, I use large elements because there is no change in color. There is no refinement needed there. And you can see that actually the picture on the right more closely resembles the image, the true image, than the picture on the left. Okay, so this is the idea of adaptive finite elements. Use refinement where really information is needed, so where changes happen fast. And okay, this is just a motivational picture. In terms of mathematical analysis, I'm actually interested in explaining a plot like this. So this tells you that doing this uniform refinement, you plot an error of a solution to a PDE with respect to the number of triangles. You would get something like here a rate n to the power minus 1 over 4. And with adaptive, you would get n to the minus 1. And the idea of optimality is that actually this adaptive algorithm produces the best possible rate. This is something I want to convince you that we can do. That actually the adaptive algorithm converges faster than the uniform. Okay, so this was the first topic. The second topic is so-called preconditioning. And the idea is, so when you want to compute something on the computer, you do some discretizations of PDEs. So I said with the finite element method. With the finite element method, you actually have to solve a linear system of equations. So a linear system of equations, AX is equal to B. And you can say, okay, I mean, mathematically, this is trivial. I just compute the inverse and I'm done. Yeah, sure, but the computation of an inverse matrix is very expensive. So it scales with n to the power 3 for the entries of a square matrix. So let's think about simulations with 1 million elements. 1 million to the power of 3 is not feasible. So in general, you use some kind of iterative method, which you probably know from your numerics course, like the conjugate gradient method or the GMRES method. So just do some iterations and compute an approximation to this X. And doing this iterative method, the speed of convergence actually depends on the condition number. So actually, the condition number of a symmetric matrix is given as the maximum eigenvalue divided by the minimal eigenvalue. And this quantity determines how fast does my iterative method, so a method of approximating this X, converges. And you want to have fast speed of convergence, then you'd have a low number of iterations, and you would have an efficient numerical method. And in general, this is not true. So in general, this iterative method does not converge fast, but you can actually help speeding it up. And this is the idea of preconditioning. Rather than solving the system AX equal to B, you would actually solve a so-called preconditioned system or the equivalent system where you multiply with a matrix P inverse on both sides. This is obviously equivalent if this is a regular matrix. And now the idea is I want to have a matrix P inverse where the condition number of the product is small, such that my iterative method converges fast, and the application of this P inverse is actually. So I can compute this way cheaper than actually really computing the inverse. So taking P inverse is equal to A inverse, I would get a condition number of 1. But the computation of the inverse is too expensive. So there's a kind of a trade-off involved. So you want to have a small condition number, and you want to have an application, a cheap application of the precondition. So these are counteracting things, but I want to convince you that we can do this in an efficient way and actually prove this plot here. So if you want, so explain this plot, not prove this plot, so that if you take a look at, so this is the simulation for a fractional PDE, and the condition number for the finite element approximation in a non-preconditioned way grows, and here the condition number would be over 1000 quite quickly. But if you do some clever method of preconditioning, you would get a condition number always bounded by 10 or 11 or something like that. So this is a nice method. It stays bounded independently on the numbers of triangles you would have in your finite element. Okay, and the final topic I will talk about is that for the finite element method, sometimes your quantity of interest is not the error on the whole domain, but only on a local subdomain. Think about the crash test, which is sometimes modeled with finite elements. So if a car crashes into a wall, then you're most likely more interested in the error in the front rather than in the back. So the question is, what can I say locally about finite element errors? And the question is, does the error actually converge faster locally where solutions are actually smooth? And this plot actually shows exactly that. So the global error in L2, for example, converges slower than the local error in L2, and even in H1. But I will explain this in more detail. So locally, you would get a better convergence. And these are all for fractional PDEs. So let's go to the precise mathematical formulation. This was just, I would say, motivation. Yeah, how is the fractional Laplacian actually defined? And yeah, I would say the most natural definition would be using Fourier transformation. So you know, the Laplacian can be defined as the so the Fourier transformation makes derivatives into multiplication. So for the Laplacian, you would have theta squared here. And we just replace the theta squared by theta to 2s and take the inverse Fourier transformation. And by definition of the Fourier transformation, which actually takes multiplications and maps them onto, and it produces derivatives out of multiplication. So this is the idea here. You would get a definition for the fractional Laplacian. But this is not really feasible for numerical analysis, I would say. It's a nice theoretical tool, but it's not feasible for approximation. So we are actually more fond of the following definitions, as so-called a singular integral definition. So there's a pointwise definition of the fractional Laplacian as a constant times this principal value integral of u of x minus u of y divided by this kernel function, which is the distance of x minus y to the power d plus 2s, where here the fractional exponent appears. It's a singular integral because when x goes to y, this blows up. But this exists in a Cauchy principal value sense. And yeah, this is an integral operator, and this is the formulation we were looking at. And there are many more definitions. And if you're interested in that, I can recommend this paper by Kwasnichev, which is called 10 equivalent definitions of the fractional Laplacian. So there are some in there which are defined using the spectral theorem, which tells you how to actually define a function operator to the power of s, or with semi-group theory, or so on. There are many more. And I should stress that they are equivalent in RD, but not on a bounded domain. On a bounded domain, they're really, especially the spectral definition and the integral definition, are completely different. And once more stressing that this is a non-local operator, so this is mathematically and numerically very challenging. Okay, so there's one additional interpretation, and since most of you are probably from PDE theory, this is interesting for you probably, and you probably know that. So it's a PDE interpretation of the fractional Laplacian, and this is also very useful for analysis. It's as a directly to Neumann operator of a degenerated elliptic PDE on a half space. So I introduce a new variable, y, and look at a solution of this PDE on RD times 0 infinity, so the new variable is only positive, and I prescribe some Dirichlet data. And the idea now is actually the fractional Laplacian up to constant, the fractional Laplacian applied to the Dirichlet data can be computed as the Neumann data of the solution of this degenerated elliptic PDE. And this is degenerate elliptic because it depends, alpha depends on S. So if alpha is actually positive, then for y equal to 0, this coefficient goes to 0. So in general ellipticity, you don't want to have that, but this means degenerate. Or in the other case, if alpha is negative, then this coefficient would go to infinity. So this is a not bounded from below and not bounded from above in the key. Depends on the case. But this is still nice, so that you can still do a lot of theory for this PDE and use the PDE theory to actually get something out for the fractional. And this is really this formulation of this so-called Caffarelli-Silvestro extension problem from this 2007 paper. Here, this formulation really produces you the integral fractional Laplacian. So rather than working with the integral fractional Laplacian, you can also work with this extension problem. And this is a nice property. Okay, so what is our model problem? Our model problem is I take a fractional PDE, so I wrote the right-hand side, f is equal to this fractional Laplacian. Again, the definition, the integral one, but I only take x in a bounded domain omega. And omega should be bounded Lipschitz. And I take an exterior boundary condition of setting u equal to 0. So this is my model problem, fractional PDE. And the Hilbert space formulation is in, I call the Hilbert space, the energy space HS tilde. And these are global HS functions. So if you want defined via Fourier transformation, and which are 0 outside of omega. So this is how the space is defined. And now the weak formulation of this fractional PDE here up there can be obtained by multiplying with the test function v and integrate. You don't need to integrate by parts, which you usually do, but this follows from, so just by doing easy formula manipulations, you get this symmetric formulation of u of x minus u of y multiplied with phi of x, and v of x minus v of y. Okay, and so you get a symmetric bilinear form, and you have tested this with all functions in the Hilbert space. You seek for a solution u also in this Hilbert space. Obviously, this exact weak solution is unknown. So in general, I mean, there are some examples where there is something known, but in general, it's unknown. So we want to compute a finite dimensional approximation to compute something. And the idea is, okay, I do a finite element method. So here's my domain omega, and I decompose it into triangles, just as I did with the picture before. And for doing adaptive methods, you need to have some more levels of refinement. So the bigger this L index is, the finer my triangles are. And this is also measured with a local measured functions, which actually returns you for each triangle the diameter of the triangle. And on each triangle, we actually approximate the PDE with piecewise linear polynomials. So they should be continuous, or in H1 on the whole omega. And on each triangle, there should be polynomials of degree. And now the Galerkin approximation is so this is something we can compute on a computer, which is finding a discrete function in this space of piecewise linear polynomials, which is a subspace of our energy space, such that my weak formulation is fulfilled when I seek for a function in this discrete space and I test in this discrete space. Okay, so this is just replacing the continuous space with a discrete space, and now I get something I can plug into the computer by using a nodal basis of this space, just the basis. This is a finite dimensional space, so I have a basis, for example, using the head functions, and plugging this into the discrete formulation produces the so-called Galerkin matrix. And now I have everything I want, and I can give you the first result of our works. And this is a common denominator of all the 3 topics I have. So we used it in every topic in some sense. So we actually were able to prove in our work in 2019, a local inverse estimate for a non-local operator on locally refined meshes. So this is something non-trivial by multiple applications of the word local. No, so yeah, and the idea is to bound a stronger norm by a weaker norm, and this always only works in a finite dimensional setting. So taking this finite dimensional space, then we were able to prove actually that this weighted norm here, so this is a norm, an L2 norm, weighted with the power HL to the S. And here we have the application of the fractional Laplacian to a discrete function, can be bounded by the energy norm of the discrete function. So this is an inverse estimate. So if you would multiply, so think about multiplication with this h to the other side, you would get a negative exponent. This is typical for inverse estimates. Yeah, but this is something non-trivial, and it's very, very useful in analysis. Yeah, and the constant here is independent of the mesh width function. This is important. Okay, so now I have everything I need for my general setting, and I will produce the results for the three topics I stated in the beginning. So let's start with optimal adaptive finite element method. So an adaptive algorithm, so I showed you in the picture before, this is just the algorithm for the picture before. You take an initial mesh, which is very coarse. You take some parameter theta in advance. So theta equal to 1 should be uniform refinement. Every other theta should produce something adaptive. And you just iterate a loop, solve, estimate, mark, refine. And in the solve step, you compute the discrete solution on the current mesh. In the estimate step, you compute some indicators which should tell you how big is the local error. So where should I do something? And where should I do something is done with a so-called marking criteria. So here we do Dörfler marking, which tells you that I take a percentage. So this is I sum up all these error indicators, and I want to have a set which actually controls a percentage, and the percentage is given by theta of the total error. And I mark these, and then in the last step, I refine all marked elements and maybe a little bit more to keep some quantities of the mesh, just as like I don't want to have any hanging nodes or something. So if you want to preserve some quality of the mesh, you maybe need to refine a little bit more, but not too much more. Okay, and this is the algorithm which actually produced the more refined picture I showed you before. So the main question about adaptivity, so maybe I should say this algorithm is really old. It goes back to Dörfler in 1996, so this is nothing new. What is new is adaptivity for the fractional Laplacian. So the question is, which error estimator should I choose for the fractional Laplacian? And this is discussed in the works by Enzo Fenclusa and Bonito Portegay, Noceto, Otarola Salgado in 2017. And they actually proposed the so-called weighted residual error estimate. So this is, you plug in the discrete solution into the equation and measure the error. And they actually measure the error in L2 and introduce a weight function here. So usually you would measure the residual in a dual norm, in the dual space. And in the dual space, okay, the dual space is an H minus space, and you want to actually have this local contributions. So this is a non-local norm. So doing this localized, you would introduce here an L2. L2 is a local space, and you would multiply with this weight to compensate for the correct scale. And they say that, and they actually prove that this is so the error can be bounded by the squared sum of these indicators. So this is so-called reliable. So this looks like a good thing to do. But this is not well defined for all S. So this is what I wrote down here. This formula is not well defined if S is too big, so too close to 1. And why is this the case? So the idea is, if you look at the fractional Laplacian, this is actually on the whole space. It's an operator which maps the Sobolev space HT to the Sobolev space HT minus 2S for any t bigger than S. Okay, so I plug in an HT function, I get an HT minus 2S function. I plug in a discrete function. So I plug in a continuous piecewise polynomial of degree 1. And one can show that these polynomials are in the solar space h3 minus epsilon for all epsilon, but not in the space where I choose epsilon equal to 0. So what tells you, this mapping property of the fraction Laplace tells you that actually, if I subtract here 2s, and if s is bigger than 3/4, I'm not in L2. So what I wrote down here does not make any sense for s bigger than 3/4. And this is actually something which this paper noticed that but they didn't correct it. They said, okay, there is no error indicator of residual type for the other case. And so our idea was, maybe there is one. We just need to measure something else. And the idea is that this blow up, which happens, this blow up happens when a point goes to a line of this, so the boundary of the triangle, this so-called skeleton of the mesh. This can be measured by power of the distance function to the boundary of the triangle. So this is omega L. This is a local distance function which I plug in a point and I compute the distance to the closest triangle. And we actually had proven a lemma that if I multiply the fractional Laplacian applied to a discrete function, and if I weight this with the weight function with a big enough exponent, then I get something in L2. So I don't have this blow up. I counteracted this blow up with this weight function. Yeah, now I can use this weight function for my area indicator. I just multiply with this weight. Okay, subtract this exponent of the weight from the powers of h, and I get an error indicator which is actually well defined for all s. And we can also prove that it's reliable. There's still an upper bound for the error, and it's actually, for the case of smaller s, it's really below the other residual error indicator. So this is a better error indicator, if you want, than the previous one, and it holds for all s. So this is a result regarding the adaptive fan. And with this error indicators, we can actually prove this theorem, which looks really complicated, but bear with me on that. So this is how usually these theorems on adaptive algorithms are formulated, going back to Stevenson in 2007, and this great work by Carstensen, Feischl, Pache, Pretorius in 2014. So this theorem actually explains this picture. So this explains why we have rate n to the power minus 1/4 in the uniform case and n to the power minus 1/2 in the adaptive. So it actually tells you for any adaptivity parameter theta, you would get linear convergence of the error indicators. This is linear convergence. If I do n steps of refinement and compute the error indicators, then I have a contraction by q to the n. So linear convergence of the error indicator. Then if I take the set of all meshes which have more, at most n more elements than a given mesh, then, and if I look for the best possible mesh in this set, so think about this is a finite problem. So I can say, if I approximate my PDE with finite elements, I can think about there is a best possible mesh, a mesh which minimizes the error, if you want. And if I take this mesh, so this would be called this optimal mesh, and the best possible error indicator I compute on this best possible mesh, and this multiplied with n to the r is finite, then our theorem says the same holds for our indicator and our mesh. So if this optimal error indicator decays with rate n to the minus r, then our indicator does this as well. So the caveat is, if the problem allows for the rate n to the power minus r, our adaptive algorithm reproduces this rate. So if the rate n to the minus r is possible, this tells you this quantity, then our indicator reproduces it. So this is for uniform refinement, this is not possible. N to the power minus 1/4 is the best possible, and n to the minus 1/2 for adaptive. Okay, and how this is proven? This is proven using an abstract framework called axioms of adaptivity. So in this 2014 paper, and this is shown with the use of an inverse estimate. this inverse estimate we have. Okay, so showing you a numerical example. So I take a step function which is 0 here and 1 here. Take a parameter of S, so there the exact solution is known and the energy is computable. So I can really look at the errors, the true errors, and this is how the solution actually looks like. And now we can see, okay, for this problem, there is the uniform rates and the adaptive rates. Both, and you can see the estimator, which is always above of the true error curves. This is for two different choices of parameters, and you can always see that the adaptive rates are n to the power minus 1/2, the best possible you can get. The uniform rates are reduced to n to the power minus 1/4. Okay, so let's go to the second topic. Time is short, so we go to preconditioning. And as I said before, so that the problem is in finite elements, also in adaptive finite elements, you need to solve the linear system. So this was something, the first step of the adaptive algorithm, you had the solve step. And now we're talking about the solve step. So the solve step is actually, you don't want to compute the inverse. So we want to do this in an iterative. This depends on the condition number. And the condition number is worse for adaptive refinement. So if you do adaptive mesh refinements, this condition number can be shown to actually grow something like that, a maximum mesh width or a minimal mesh width to some power, multiplied with n to the 2s over d. So this is not only an upper bound, you can also prove that there is a lower bound. And yeah, you can say, okay, I mean, then I do something like diagonal scaling. I take the inverse of the diagonal of the matrix. Okay, yeah, this helps you, it gets rid of this first guy. But you still have this dependence on n to the 2s over d. So for big N, this gets bad as well. So the question is, which preconditioner can I choose such that the condition number stays bounded, independently of the number of triangles or the mesh size I have? And the answer is, you can actually do an abstract adaptive Schwarz preconditioner. So you can do, and here's the abstract theory, which actually can be found in the book of Toseli and Widlund. And I should mention the paper by Feischl-Führer, Brodors, and Stefan in 2017, where they did something similar for the boundary element method. And for the abstract adaptive Schwarz theory, you need to define two things. You need to have a subspace decomposition. So we take here the finest grid, and the piecewise linears on the finest grid should be decomposed into some subspaces, which you need to write down. And on the subspaces, you need to have a so-called local solver. So you need to define a bilinear form AL, so local bilinear form. And doing this, the general theory tells you, if you have two things, then you're done. If for every piecewise polynomial, there exists a so-called stable decomposition. So I can decompose this polynomial with respect to the space decomposition, such that I can actually bound the sum over these local solves by the A of UU, by the global bilinear form and the function I plug in. Then I get from the theory of Toseli and Widlund that the minimal eigenvalue of this precondition system, so I will define the preconditioner on the next slide, but the preconditioned system, which corresponds to this abstract theory, produces a lower bound for the minimal eigenvalue. And the second thing is, so for any decomposition, we actually can produce the other estimate if you want. So here there exists one. Now I take any arbitrary decomposition. I can bound A of UU by the sum of these local solves. Then I get an estimate for the maximal eigenvalue of the preconditioned system. Okay, so this is what you have to abstract in the way. So you can actually prove this abstract setting for the fractional Laplacian. So how do we do that? How is the realization? We take one node of the mesh, we take the corresponding basis function, the head function, and we take the set of all the new nodes and direct neighbors when we did refinement. So I did refinement, so I get some new nodes, and I take these new nodes and all the direct neighbors in the mesh. and define my space decomposition as the span of all the basis functions corresponding to this new nodes when I did refinement and the direct neighbors. And this is a spaces of uniform submeshes. And this local solvers, there's AL I need to define, and for us these were local realizations of the HS norm, so in a weighted way. Okay, it's not too important, but you can actually also use if you want the exact ones. And yeah, UL is actually the local solution of AL, UL, VL is equal to FVL. So the local bilinear form and locally tested on this subspace decomposition. And now you can define the preconditioner just by summing up this local solution. So this is why I think about a subspace decomposition. So think about this as subspaces, and I sum up the local solution on the subspaces. This is the idea of adaptive Schwarz. Yeah, and the matrix representation of this precondition I wrote down here on a functional level produces this matrix p to the minus 1. And you have to pass on that, but this is a so-called local multi-level diagonal scaling. You can write down a formula for that. And so you only sum up some diagonal matrices. And this is cheaply computed. So diagonal matrices are cheap to compute. So I hope to have convinced you that you can compute this precondition in a cheap way. And the theorem, which I wrote down here, is we are actually able to prove this two crucial quantities, which I said from the abstract theory. You need to prove that there exists a stable decomposition, and you actually also need to produce that for all decompositions you have the converse estimates. And our theorem says, okay, with our decomposition, subspace decomposition, and our local source, you can actually produce these two estimates, and the abstract theory then gives you a bounded condition. How do we get there for this theorem? Just the ideas of proof. For the lower bound, we actually produced some novel stability estimates for the Scott-Sang projection in Bezoff spaces. If you don't know anything about what I said, ignore it. For the experts, they know probably what I mean. And for the upper bound, we used our inverse estimate as did exactly in the beginning. There was this inverse estimate for the fractional Laplacian on the space P10. And this directly produces the answer. Okay, and yeah, this works both for the adaptive mesh hierarchy and even for an artificial hierarchy, which you can actually, if you have only a mesh given by your application, you can produce your artificial hierarchy by looking for the mesh and finest common coarsenings with uniform meshes. So this is maybe more in sense of applications, that if you get one mesh from CRD, you can actually produce an artificial hierarchy. And with this, we can also prove the general theory. Yeah, and this theorem above directly produces the bounded conditional number. And this directly explains this plot here. So here, in the non-preconditioned way, I get some growth. This is what I stated in the beginning, this maximum or minimal mesh ridge multiplied with the number of triangles. And for our preconditioned case, I get a condition number independent of the number of degrees. Okay, so finally, not more than 10 minutes for the last part, for this local error analysis. So what is the setting here? So you think about, I had this local source in the preconditioned setting. So the idea is, what can I actually say locally about the finite element method? And think about only just the Laplace equation, so the Poisson equation, not fraction, just the Poisson equation. And the idea is, for a Poisson equation, we know that the solution is inside a domain is usually smooth. So if F is smooth, so you only have singularities at the boundary. So the question is, if the solution is locally smooth, can I get faster convergence locally? So on subdomains away from the boundary, for example. And yes, the answer is yes, and this goes back to Nietzsche and Schatz in '74, or Warbin in 1991. So this is also all results for the Poisson equation. So that improvement is possible since we have a local estimate. And so the local H1 error can be bounded by a local best approximation error. This is the first guy. And if you have higher local regularity, this term actually converges faster. It's a local term, so it does only depend on how regular my solution is locally. And second guy here is a weaker norm. So by doing some kind of duality arguments, you can also hope for, since this is a weaker norm than this one, you can hope for faster convergence. So this is why you actually get better convergence rates locally for this problem. So the idea is, can we do something similar for non-local operators? And what about the rate of convergence? And for integral operators with the boundary element method, yeah, this was done. There were sharp estimates and faster local convergence, which went back to Saranen and Stefan and Gran. And yeah, we improved the results by really proving sharp estimates in 2018 for the boundary element method. Yeah, and for the fractional Laplacian, actually, in the same month as us, there was a preprint by Noceto and some co-workers, where they also answered the same question. But luckily for us, they only looked at the energy norm, and their estimates were not sharp for small s. And in our work, or in this talk, we actually had sharp local estimates, and we also looked at stronger norms than the energy. So we actually completely answered this question. And here's the theorem actually for the fractional Laplacian. So again, the setting is, think about omega being somewhere out there. We take two subdomains, which are apart, and we assume that U is at least H1 regular locally. Then we can actually prove that the local error in H1 can be bounded by the local best approximation in H1, plus here it is a global term in a weaker norm. For the Poisson equation, it was a local term in a weaker norm. But this is due to the non-local effects of the fractional Laplacian. Yeah, and this hidden constant depends obviously on the choice of subdomains, but not on the mesh size or something like that. And yeah, due to the non-locality, we have this global term. And an analogous result also holds for the energy norm. So I can plug in here the energy norm HS tilde, and this would remain the same. Okay, since so what is the main idea of our proof? So the main ingredient, which is completely different than the work of Noceto and his co-workers, is that we actually use localization with cutoff functions. Okay, I mean, this is also what Noceto does, but so we take functions which live on the smaller, which are one on the smaller domain and live on the bigger domain on the inside of this one. But we actually look at localized versions of this non-local operator. And localized versions are actually so-called commutators. And so-called commutators are, I interchange the cutoff function with the operator and take the difference between these operators. So this obviously is not a zero operator. They don't commute. This is an integral operator, and this is a function. But this operator has favorable properties in the sense that it is a weaker kernel singularity. So the singularity of this kernel is actually weaker since you take the difference of a smooth function here. So this cutoff function is smooth. So this difference would cancel you out one power in this denominator. So rather than the fractional Laplacian I stated before, is an operator of order 2s. So you plug in a function and you lose 2s derivatives if you want. But here, if you plug it into the commutator function, you lose two derivatives, but you gain one back by this smoother kernel. So it's an operator for the 2s minus 1. And this is what this lemma actually tells you. So ignore this theta, so this holds by adding additional parameter, but this tells you that if you plug in an hs minus 1 function, then I get an h minus s function. So this is actually the difference between these exponents is just this 2s minus. And this actually gives you something, produces this global term in the weaker norm. Yeah, and the proof actually relies on some Fourier techniques. So, okay, so I will skip this, send them late. So the main ingredient, second main ingredient is this Caffarelli-Silvestre extension problem. So this is second to last slide of mathematics. So with this Caffarelli-Silvestre extension problem, we were actually able to prove some interior regularity of this problem, of this extension problem. This is also crucial. So if the data, the boundary data, and the bigger box here is separated, then one can actually prove that the second derivatives in a weighted L2 norm for this problem can be bounded by the first derivatives on the larger domain. So this is also, yeah, this is even better than an inverse estimate, I would say, because there's no mesh dependence here. So you can actually estimate second derivatives by first derivatives. So this is really nice. And this also helps us to obtain this term in a weaker norm. Maybe for the proof of that, this is the technique of tangential difference quotients. So you take a clever test function, which is actually a local difference quotient, and which actually uses this support property. Yeah, and now the last slide of mathematics. What can I do with this local estimate? So this is the local estimate we were able to prove. Now, assuming that our function has higher local regularity, so it's in h1 plus beta on this subdomain, then the first guy, this is the best approximation term. This just depends on this local regularity, so this produces you an error order h to the beta. Okay, so let's say we assume we have some global regularity. So hs is the energy space, and let's assume we are in hs plus alpha for some alpha bigger equal than 0. Mind you that in comparison to the Laplacian, alpha cannot be bigger than 1/2, even for smooth omega, because fractional operators have singularities at the boundary. But okay, with this additional alpha, a duality argument in this term in the weaker norm produces you an order of 1/2 plus alpha minus epsilon. And as a corollary, we can actually prove that the finite element method converges locally with order minimum 1/2 plus alpha minus epsilon and beta. So comparison with the global, so yeah, I'll show you one picture. So an exact solution for the problem on the unit circle is given by this function. So the positive part of 1 minus absolute value of x squared to the power of s. And this function has regularity 1/2 plus s minus epsilon. So if s is small, this function is not in h1. So I would not get any convergence in h1 globally. So this is for the case s equal to 0.3. But I even get local convergence in h1 of order 1, as predicted by our theorem. And okay, in L2 I get some global convergence, but I even get faster local convergence. And the rate is the same as for the h1 convergence. So by interpolation, I also get the same rate for the hs energy norm. And I cannot get any better rate because this global term in the weaker norm is the same for the L2 estimate and the h1 estimate. So I cannot gain anything. And the other plot here tells you if I increase my s, then okay, I get some global convergence in h1, but this is very slow, but locally this is very fast. So the local behavior is much better than the global behavior if I am away from the singularity. This is what we can prove, and this is what we can observe. Okay, and so let me conclude. What did I show you? I showed you at first a novel, very useful inverse estimate for the fractional Laplacian. So if you're doing numerical analysis, for a fractional Laplacian, you can probably use that. For the first part, I showed you a new reliable error estimator for large parameters S, and optimal convergence for an adaptive algorithm for finite elements applied to the fractional Laplacian. Then I showed you an optimal preconditioner on some locally refined meshes. And finally, I showed you some sharp local a priori estimates for the Galerkin error. And the local rate of convergence in H1 can be proven to be h to the minimum of 1/2 plus alpha and beta. So the local and global regularity come into play. Yeah, and some future work regarding that would be a speed up of computations of the error indicators for the adaptive method, since the computation of those are really slow, and looking at other error indicators, for example, and maybe producing all the results for the spectral fractional Laplace, which is completely different. So this is future work. And with this, thank you for your attention. And if you're interested in our work, everything is on Arc. Thanks.
Thank you, Markus. Very interesting. And you are on time, I would say. Yeah. Thank you very much for not taking too much time. I would like to ask the participants if you have any questions for Markus.
We just start talking?
Yeah, I mean, I would say so. If there's too much chaos, I would ask you to raise hands, but
Okay. Yeah.
just, Norbert, go ahead.
Yeah, very interesting, the presentation, Markus. Thanks a lot.
Thanks.
Particularly, I like the local error estimates. Very, very impressive. So when I think back to my times when people started doing boundary elements and three-dimensional surfaces, now you are doing fractional Laplacian also in 2 dimensions and 3 dimensions. Do you know whether anybody is working on graded meshes or more generally anisotropic elements? Because that was a big topic back those times, but I haven't seen that people are working on that for fractional operators. Do you know anything about that?
Yeah, that's actually something we want to work on. But we, so I know that Hans-Peter Stephan is working on that, and he actually asked us to do a cooperation for doing the preconditioning stuff on anisotropic meshes. So this is something we hope to work on next year. So graded meshes is something which is done. So finite element for graded meshes, not isotropic graded meshes is done. So this is by Nochetto and his co-workers, but anisotropic is a completely different question. So there are no results available to my knowledge, but this is really something we want to work on. EBS wants to work on that, and I also think Nochetto wanted to work on that, but this is right now it's a little bit out of reach because, yeah, you know, this gets messy. So all the errors depend on the shape irregularity we have there. But you can track that and you can hope for some estimates for that. But this is really in the future.
That also means the local inverse estimate is only just for shape regular elements, right?
Yeah. Yeah, this is also for shape regular elements. Everything I presented to you is for shape regular elements. And this also explains, maybe where's my plot? So here you can see that the best possible rate which you achieve with our adaptive algorithm is n to the -1/2. This is not what you would expect with P1 elements. You would expect something like 2 or 3. So this comes from this is just because we work with isotropic meshes, and if we would hope for an adaptive method on anisotropic meshes, which actually produce you really the best possible rate you can hope for with piecewise linears in terms of approximation.
Yeah, thank you.
Thank you. Are there any more questions?
Yeah, I have a question.
Yeah, go ahead.
So you compute on the unit circle. What kind of do you use curved elements, or what kind of elements?
Yeah, thanks.
Or an approximation of the boundary.
Yeah, I do boundary approximation. So this is actually a variation of crime I'm doing, but I actually refine the boundary approximation as well. So I'm using so I'm using a FEM code. I think I added to the, yeah, I'm using a FEM code by Acosta Bortakarai, and yeah, this FEM codes is actually not using curved elements, but yeah, in every refinement step you also refine the boundary approximation, and this is of higher order. So this is something, for example, we can look at Michi Feischl's PhD thesis, where he actually showed that boundary approximation is higher order. The same arguments can be applied here.
Okay.
Thank you. Are there any more questions?
Yeah, sure. Now I have another question. But just for the model problem, do you know if there is some kind of other model problems that use fractional Laplacian with a negative power of S?
Negative power of S.
Just for just for interest.
No, I actually don't know. I've only seen it with positive powers. Yeah, maybe there sure are some, but I cannot give you any example. Sorry.
Okay, good question. Any more questions? Well, I have a question. So, if I'm not mistaken, if you, for example, if you look at the general elliptic operator, for example, minus Laplacian plus identity, and you take a power of S, I think you can treat this with the Causality-Silvestre approach. Is that right?
Yeah. You can do that. Yeah.
Is there something similar? I mean, can you do this also with the integral approach? I mean, can you take the power of S of a general elliptic operator and?
Yeah, you can also do that with the integral approach. You have a different kernel function then. Yeah, but this is doable.
Yeah. So okay, that was my question. So maybe we can speak later because that would be something interesting.
Yeah. I mean, this. Now I haven't seen it in literature. That's true.
I mean,
Laplace
that's why I'm wondering. I also haven't seen it. So well, we can talk about that later maybe.
Yeah, maybe. So I think so. In general, taking more involved fractional operators, so fractional Laplace is the easiest, but other fractional operators are also open questions. Many open questions for that.
So you would say that this fractional business is still interesting in terms of.
For me, it is. So I don't know if it's for you.
No, I mean in terms of a lot of open questions.
Yeah, right. There still are. I mean, Norbert has probably asked the most important open question, but yeah, there are also many more. So.
Okay. Thank you. So, are there any more questions for Markus?
No, we're just waiting for the invitation to the wine reception.
Yeah, please send me the wine over here.
Well, I should mention that next week we have the next seminar, so 5th of November. Roberto Morales will talk about the results on controllability of parabolic equations with discontinuous coefficients. So that might be something very interesting also. So I hope to see you there. And if there are no more comments or questions, then see you soon. Thank you, Markus. And
yeah, thanks. Thanks for having me. So it was a pleasure. Yeah.
So goodbye, everyone.
Bye-bye.
Bye-bye.
Bye-bye.